section 7.3 today. Section 7.3 has a lot going on, so we're going to be simplifying. We'll also be talking about the distance formula. And we'll be finishing with circles. There's a lot to radicals, so what we'll do is we'll just do one property at a time. So the first property is called the product rule for radicals. And the product rule says that the nth root of A times the nth root of B is equal to the nth root of A times B as long as n isn't even and A and B are not both negative. We'll just get into this with some examples. I'll just ask you to multiply. And let's say we had the square root of 5 times the square root of -3. You're allowed to do this because even though the index is even, both numbers aren't negative. So this is totally fine if you want to do the square root of -15. You could also do the square root of 7 times the square root of xy. And that's equal to the square root of 7xy. So you're allowed to combine two radicals, again, as long as the index isn't even and at the same time both numbers are negative. That's the only case where you can't do this. You could also do it if it's a cubed radical, like the cubed root of 2 times the cubed root of 7 is equal to the cubed root of 14. Or if you had the 6th root of 8r squared times the 6th root of 2r to the 3rd, you can combine what's inside those radicals, as long as they're not both even and the index is even. This would just be the 6th root of 16r to the what power? To the 5th. R squared times r to the 3rd is r to the 5th. Most complicated kind of problem you'll see is if we have the 5th root of 9y squared x times the 5th root of 8xy squared. It's 8 is 72. Anytime we multiply the same base, we add their exponents. So x times x is x to the 2nd. Y to the 2nd times y to the 2nd is y to the 4th. couple examples that you can't do. You can't do something like the square root of 7 times the cubed root of 5. If the indices are different, you're not allowed to combine these. So we just say that they cannot be simplified. And I kept telling you about the even root and the negative radicands. That would be like something like this. If we had the square root of -2 times the square root of -2, you're not allowed to say that this is the square root of 4. It doesn't work like that. Because these are even, and we have both radicands are negative, this also cannot be simplified. So that's called the product property. The next property is called the quotient rule for radicals. And the quotient rule says that if you're taking a radical of a fraction, this just means you're taking that radical for the numerator and that radical for the denominator. If the directions were just to simplify, the square root of 100 over 81. This is really just two problems. The square root of 100 over the square root of 81 is just 10 over 9. That would be the answer. The square root of 11 over 25, similarly, is just the square root of 11 over the square root of 25. Square root of 11 simplify, it's not a perfect radical, but the square root of 25 is. We could just say square root of 11 over 5. We're going to mix things up a little bit. Say if we had the negative cubed root of 1 over r to the 12. That negative has no bearing on anything. It's just along for the ride. We're really just doing the cubed root of 1 over the cubed root of r to the 12. Cubed root of 1 is just 1. In our last class, we talked about radicals and exponent powers. So does anyone remember the cubed root of r to the 12th? What would that be? Talked about a property converting radicals to fractional powers. 12 over 3 is correct. So there was a property that said if you have the nth root of x to the m or the nth root of x to the m, these really are the same thing. That's the same thing as x to the m over n power. We just have to try to remember all these properties. So in this case, we could simplify this by just saying r to the 12 over 3. 12 over 3, of course, is 4. We had the cubed root of negative 27 over 64. This is just the cubed root of negative 27 divided by the cubed root of 64. You can use your calculator for this if you don't remember perfect cubes. But the Cube root of negative 27 is just negative 3. Cube root of 64 is just 4. Next example like this is if we had the fourth root of y over 81. Sometimes things can't be simplified and you just leave them alone. So this would just be the fourth root of y over the fourth root of 81. Fourth root of y can't be simplified. The fourth root of 81 is just 3. One thing that we're going to spend a good amount of time on tonight is simplifying imperfect radicals. So one thing that I'd like to do is I'd like to just write the rules down and then explain it more with numbers. Sometimes in math, it's easier to explain with numbers than it is with words. So there's 4 rules in order to do this. The radicand's power has to be less than the index. So for example, the cubed root of x to the second is good, but the cubed root of x to the fourth is bad. That means we could simplify it more. Second property is that the radicand has no fractions. We had already seen if you have a fraction, we talked about how to handle it. We just distribute the radical to the numerator and the denominator. 1/2 would be the answer. But inside the radical, there are no fractions. That would mean that it's fully simplified. Third rule is that no denominator has a radical. We have to do something called rationalize. We'll see that in the coming lessons. The last property says that exponents in the radicand and index have a GCF equal to 1, which means they can't be simplified. We talked about converting radicals to fractional exponents, and you just want to make sure that that fraction is completely simplified. So let's go through some of these here. First step is I want to talk about how to simplify imperfect roots. I'm going to show you 2 ways to do this. Sometimes it's more convenient to use one, sometimes it's easier to use the other. But I'll show you both ways, and I'm going to use both techniques. So I would want you to be able to understand what I'm doing here. Let's take a look at the square root of 18. Obviously, square root of 18 is not a perfect square. So there's two different ways that we could do this. One technique we could use is called the prime factorization tree. Using it this way, most people do this. I would say maybe 90% of people use this way. It gets you the right answer every time, but it might take a little longer. So prime factorization tree just says break down the radicand to all prime numbers. Smallest prime number. Prime numbers start at 2. So 2, 3, 5, 7, 11, 13. You're not really going to have any prime numbers bigger than that. 1 is not a prime number. Most people would say, 1 is a prime number. It's not. So the smallest prime number is 2. So if we take a look at the square root of 18, what we're going to do is we're going to write our groups on the outside, and we're going to write what's left over on the inside of the radical. So let me show you what I mean. With the square root of 18, we're going to break 18 down to prime numbers. So I know that 2 goes into 18 9 times, so 18 is 2 times 9. 9 is the same thing as 3 times 3. So right at this point, 18 is broken down. 18 is the same thing as 2 times 3 times 3. We're looking for groups of the index. So for example, the index is 2 here, square root. We're looking for a group of 2 of the same numbers. The way we simplify the square root of 18 is we write the group on the outside, and we write what's left over on the inside. This is one way to do this problem, is using the prime factorization tree. Now, obviously, the numbers are going to get a little bit bigger, but I'll show you with a smaller numbered example. The second technique that we could use is by using perfect radicals. What I mean by perfect radicals would be like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Or using perfect cubes, like 1 cube, 2 cube, 3 cube, 4 cube, 5 cube. We're never really going to go more than 5. In order to simplify the square root of 18, we're looking for a perfect square. The largest perfect square that can go into 18 would be what? What's square is 16? So we want to do 18 divided by 1, divided by 4, divided by 9, divided by 16. What's the largest of those numbers that we could divide into 18? 9, right? So we could write this, the square root of 9 times the square root of 2. We're looking for the largest perfect square to go into 18. Square root of 9 is just 3. That's the same answer we got before, but it required knowing perfect squares, and it's a little more advanced to do that way. Most people prefer to make the prime factorization tree. Let me show you another example. We'll actually just do a bunch here. I'll say to simplify. Let's do the square root of 200. Use a small number, we'll use a big number. So first thing we could do is use the prime factorization tree. It works every time. It's a little longer, but it's a reliable way to get the answer. So 200 I know is 2 times 100. I know 100 is the same thing as 10 times 10. 10 is the same thing as 2 times 5. So we break the radicand down to all prime numbers. 2, 5, 2, 5. We're looking for groups of 2. Here's a group right here. That's a group. We have a group of 5s. And what's left over? 2, right? So the answer would be 10 square root of 2. That way works all the time. No matter what we do, prime factorization tree always works. Another way we could do this is, does anyone see a perfect square that you could divide into 200? So you could divide by 25, but there's actually a bigger one that goes into that. 100, right? Yeah. So this we could write as the square root of 100 times the square root of 2. Square root of 100 is just 10 root 2. You get the same answer. It's a little quicker, but it's a little more advanced to do it that way. Let's get practice doing 2 more of these. How about the square root of 32? What I'm going to do is I'm going to use the prime factorization tree because I think that's going to be the easiest technique for most of you. It's faster to do it the other way. What's a perfect square that goes into 32? 16. So this is the same thing as square root of 16 times square root of 2. The answer is 4 root 2. But that requires that you're quick with knowing the perfect squares. You could always do a prime factorization. 32 is the same thing as 4 times 8. 4 is the same thing as 2 times 2. 8 is the same thing as 2 times 4, which is 2 times 2. So 32 is just a whole bunch of 2's. And we're looking for groups of 2 here. Here's a group. Here's a group. And there's one left over. And when we go to write this, remember our groups go on the outside, and what's left over goes on the inside. So we have a group of 2, we have another group of 2, and then we have a 2 left over. Gives us exactly the same answer. I'm not going to give you a question like this on the quiz. Like, say if you had the square root of 35. There's no perfect roots that go there, just 5 and 7, which are already prime numbers. So if there's no groups that we could take out, we say that this cannot be simplified. We'll do a couple more, and then we'll throw some variables in here. What if we had the cubed root of 54? The index tells you how many have to be in the group. We have to have a group of 3 here instead of 2. So is there a perfect cube that goes into 54? Look at the list that we made. Well, which of those goes into 54? 27 does. So if you want, the more advanced technique would be the cube root of 27 times the cube root of 2, which would just be 3 cube root of 2. But if you'd rather not be bothered with that, we can get the same answer using our tree. 54 is just 2 times 27. 27 is 3 times 9, which is 3 times 3. We have a group of 3's right here. We write 3 times the cube root of 2. One thing I just want to caution you with is if you don't write the 3 there for the index, technically that's a different answer, so that wouldn't be correct. If you're simplifying the square root, you write the square root. If it's a cubed root, you write the cubed root. Nothing really changes if you have the fourth root. Negative fourth root of 243. I have no idea what fourth root goes into that, so I'm going to have to use the tree here. 243, I think 3 goes into that, so 243 divided by 3 is 81. 81 is the same thing as 9 times 9, which is 3 times 3. So this is a fourth root. We're looking for a group of 4, and then we have a 3 left over. So the answer would just be negative 3 times the fourth root of 3. That's how we would do a problem like that. I want to show you what it looks like with variables now. So it's going to be the same thing as with numbers. So just try to watch here. What if we had the square root of x to the 5th? Like before, there's a couple different ways we could do this. We're looking for groups of 2, right? So just like with numbers, I'm going to write this 1, 2, 3, 4, 5. And I'm looking for groups of 2. We have one group of x's times one group of x's with an x left over. Or x squared root x would be the answer. Another way we could do it, that's a little bit faster, but again, it requires you remember an extra shortcut, is if you have the nth root of a, or let's say the nth root of x to the n. What we could do is we can convert it to a mixed fraction. And then the answer would be x to the a times the c root of x to the b. You don't have to do it this way. It's a little bit faster. So for example, for the problem that we just did, this is the square root of x to the 5th, which is just x to the 5 over 2, or 2 and 1/2 if we write it as a mixed fraction. So using this property, we're just going to write x to the 2nd times the square root of x to the 1st. This 2 goes here, this 2 goes here, and this 1 goes here. You don't have to do that. It's one extra thing to remember, but that would be useful if you had like the square root of x to the 50th. Right? Are you really going to sit there and draw 50 x's? I'm not going to put that on the test, but I do want to show you alternative ways in case anybody prefers one over the other. What if we had the square root of 25 times p to the 7th? This is really 2 problems in one. We have the square root of 25 times the square root of p to the 7th. Just to separate it, of 25 is 5. And then p to the 7th, this is an example where we could do it one of two ways. If you want, you could write p 7 times. Looks like there's 1, 2, 3 groups with 1 left over. That would be the answer. Another way to do this is to say that this is the same thing as p to the 7 halves, which is p to the 3 and 1 half, or p to the 3rd times the square root of p to the 1st. What if we had the cubed root of negative 27, y to the 7th, x to the 5th, and z to the 6th? It's really the same thing as 4 separate problems. Don't try to do it all at once. It'll just be confusing. We'll just write this individually. We'll write this the cubed root of negative 27 times the cubed root of 1 to the 7th times the cubed root of x to the 5th times the cubed root of z to the 6th. Cubed root of negative 27 is just negative 3. Cubed root of y to the 7th, we have a couple different ways to do that. I think most people would write y 7 times. It looks like we have 2 groups with 1 left over. So we say 2 groups, or y to the 2nd, with 1 left over. With the cubed root of x to the 5th, if you do it the more advanced way, you know that there's 1 group with a remainder of 2. So you could write this x to the 1st times the cubed root of x to the 2nd. 5 over 3 is 1 2/3, so that's using the more advanced technique. If you don't care about the advanced technique, just write it out 5 times. 1 group with 2 left over. And the last one, we're looking for groups of 3, and there's 6. 1, 2. There's nothing left over. Nothing goes inside of a radical. The way you would write your final answer is you would multiply everything on the outside times everything on the inside. So this would just be negative 3 times x to the 1st, y to the 2nd, z to the 2nd, times the cubed root of x to the 2nd y. We typically write these in alphabetical order. That's the harder part of tonight's lesson. So if you understand that, it's kind of downhill from here. As far as difficulty. Excitement is staying the same. So let me show you how to simplify just some different scenarios here. So if we're going to be simplifying using lesser indices. All this means is that we convert to rational exponents. And simplify it. What I mean is, if you had the 12th root of 2 to the third. A little different because if you wrote 2 3 times, you wouldn't have groups of 12, right? But one thing that you could do is just write this 2 to the 3/12 power using the property we talked about in the last class and during this class. 3 over 12 is the same thing as just 1/4. Throw it back into radicals. The 4th root of 2 to the first would be the answer. We never want to have a rational exponent. Like this would not be an acceptable answer on the test. You always want to convert it back to radicals. If we had the 6th root of t to the second, we could just write this t to the 2 over 6, or t to the 1/3, which in simplified form would be the cube root of t. Just to keep you on your toes a little bit, the 6th root of t to the 10th. Technically, you could write t 10 times and then take out a group of 6. So there's a couple different ways to do this problem. One way is to write t 10 times. You have one group with 4 left over. And then write this t to the 4 over 6, which is just 2/3. So the best answer would be t times the cube root of t to the second. That's one way to do it. That'll get the job done. It's just a little longer. Another way we could do this is to say this is t to the 10 over 6, which reduces to 5 over 3, which is just 1 and 2/3. We talked about this earlier. I told you this was a little more advanced, but this will be written t to the first times the cubed root of t to the second. Same exact answer, a little bit faster to get there. Go over how to multiply radicals with different indices. I'll just show you a couple of these. One, what we typically do is we convert rational exponents, and we get a common denominator. And we add. So, say if we had the square root of 5 times the cubed root of 4. This is really just 5 to the 1/2. This is just 4 to the 1/3. In order to combine these, we have to get the same denominator. That would really be what the radical is. So 2 we could just write as 3 over 6. 1/3 we could just write as 2 over 6. So this is the 6th root of 5 to the 3rd times the 6th root of 4 to the 2nd, which is just the 6th root. 5 to the 3rd is 125. 125 times 16 is 2,000. To be able to combine radicals. Let's just adjust one thing in your notes here. I said to add. I should have just said multiply. Multiply 5 to the 3rd times 4 to the 2nd because they have the same radical. One more of these. What if we had the 4th root of 2 times the cubed root of 2? I'm only allowed to multiply them if they have the same index. So we'll write 2 to the 1/4 times 2 to the 1/3. Get a common denominator, which would be 12. Get the 12th root of 2 to the 3rd times the 12th root of 2 to the 4th, which is just the 12th root of 2 to the 7th. And 2 to the 7th is 120. That's how you combine those. That's as far as I want to get with radicals tonight. We have a couple other things to talk about, Pythagorean theorem and circles, but in our next lesson we'll be going a little bit more in depth with radicals, adding and subtracting, multiplying and dividing. For tonight, that's it there. So shifting gears, I wanted to talk about Pythagorean theorem. One thing as an instructor, I don't like to just tell you this is what the formula is and memorize it. So I will ask you if you're curious. I don't want to spend class time giving you a proof of this. We could spend class time doing other things, but if you're curious on where the Pythagorean theorem came from, you could always just check that out on my YouTube channel. But the Pythagorean theorem says if we have a right triangle in A, B, and C, the Pythagorean theorem would say that A squared plus B squared is equal to C squared. So a couple examples using this. Examples here. If I told you that A was 14, B was 14, and I asked you to find C. This formula is a little more straightforward. We could just plug it in. So if A squared plus B squared is C squared, we'll do 14 squared plus 14 squared. Calculator, 14 squared is 196. Adding those together. When you go to take the square root of this, we get an imperfect radical. Just learn how to do that. So let's simplify the square root of 392. 392 is the same thing as 2 times 196. 196 is the same thing as 14 times 14. 14 is the same thing as 2 times 7. It looks like we have a group of sevens. We have a group of twos. And then we have a 2 left over. So C would be 14 times the square root of 2 for this example. One more with Pythagorean theorem would be if A is equal to 4, we don't know what B is, and C is equal to 6. Using Pythagorean theorem to plug these in, 4 squared plus, we don't know what B is, we'll just call it B squared, is equal to C squared. This would be 16 plus B squared is equal to 36. Factoring 16 on both sides. Go to square root. Is really just the same thing as square root of 4 times the square root of 5. Also done the time factorization tree, small enough, I'm sure you would have gotten the same answer. Couple more topics tonight. One is called the distance formula. This is another one where the proof, see where it comes from. The distance formula, it does come from Pythagorean theorem. So just if we had a right triangle, say if we have 2 points, one point has the coordinates x1, y1. The second point has the coordinates x2, y2. This distance is nothing more than the hypotenuse of the right triangle. So using the Pythagorean theorem, the A value would be x1 minus x2 squared. The B value would be y1 minus y2 squared. And the C squared is what we're looking for. We take the square root of both sides and wind up with your distance formula. Do a couple problems where we have to find the distance. Distance -1 and 5, 3. the distance formula, all we really have to do is just subtract the x values. So you could label them as 1, x1, y1, x2, y2, and then subtract them. So then 5, or it doesn't matter what order you do them in. 2 minus 5 squared plus negative 1 minus 3 squared. Which is negative 3 squared plus negative 4 squared. 9 plus 16 is 25. The distance is 5 units. Whenever you're talking about distance, you want to just make sure you put units. Distance. I said, what's the distance from here until Island? You wouldn't say 80, you would say 80 miles or whatever. One more of these and then we'll finish with circles. We had, let's say, negative 3 comma 2, and 0 comma negative 4. This is x1, this is y1, this is x2, this is y2. And the distance would be 3 minus 0 squared plus 2 minus negative 4 squared. Remember, you're subtracting, so if you subtract the negative, it just turns into negative 3 minus 0 is just negative 3 squared. 2 plus 4 is 6. 9 plus 36 is 45. I talked about how to reduce this. This is just the same thing. If you want prime factorization tree, 9 times 4, 9 is 3 times 3. Or this is just the square root of 9 times the square root of 5. Which, either way you do it, you wind up with 3 root 5 units. One more little topic before we leave. They're all related. I want to talk about the equation of a circle. And center, radius, form. Now, the equation of a circle comes from the distance formula. So the definition of a circle is all points that are the same distance from the center. You don't have to know this. I'm just trying to give it a little more context. So every point that's the same distance away from the center is called a cube. The collection of those points is a circle. Let the center be h, point on the circumference of the circle be x, y. And using the distance formula, x minus h squared plus y minus a squared equal the radius squared. That's just the distance formula, which is the Pythagorean theorem. They're all the same thing. One thing I just want to point out is that the center of our circle is is going to be h comma k, and the radius is going to be right. I wanted to do just 3 quick examples. It only take about 5 minutes, and then we'll get out of here. So, write the equation of a circle with one, the center is at 0, 0, and the radius is 4 units. We're going to plug in 0 for h, 0 for k. The radius is 4, we're just going to square it. So we just get x squared plus y squared is equal to 16. That would be the equation of a circle. Very simple to do. And if we were going to graph it, the center's at 0, 0, you just go 4 units out in all directions. Just do your best to connect them in a smooth way. That's how you do it. We have a circle center at 3, -2, and the radius was 3 units. Similarly to what we just did, say x minus 3 squared plus y minus -2 squared equals the radius. Make sure you're careful. It's y minus the k, so we're subtracting a negative. X minus 3 squared plus y plus 2 squared. That would be your equation of the circle. When we go to graph it, the center is going to be at 3, -2. The radius is 3 units. You just go up 3, to the right 3, down 3, and to the left 3. And then try to connect them as smoothly as you could. Last example tonight, I gave you an equation. The equation was x plus 2 squared plus y minus 4 squared is equal to 10. The center be. Remember, when we're doing this, it's x minus the h value. So this is really just x minus -2. I'm doing these equations, I tell people just take the opposite of whatever's inside. So if it says x plus 2, we're going to go with negative 2. If it says y minus 4, we're going to go with positive. What would the radius be? So the radius would just be, remember the formula, right? Turn it down a little bit more. Formula says it's x minus h squared plus y minus h squared. So the radius squared would be 10. Just give you a radius equal to the square root of 10. The radius doesn't have to be a perfect radical. So we could graph this. It's not going to be perfect, but we'll go negative 2 and then up to 4. Square root of 10 is a little bit more than 3.